Right, so thank you to the organizers for the invitation. I thought I'd give two kind of case studies highlighting broad methodological directions using machine learning for data analysis towards new physics searches, simulation-based inference, and generative modeling. So on the simulation-based inference side, I'll talk about some work on inferring the dark matter density profile from dwarf galaxies using simulation-based inference. And on the generative modeling side, it'll be about learning the distribution of galaxies, so galaxy clustering, and using it for emulation and inference. So starting off with simulation-based inference, or SBI. Simulations are a workhorse in a lot of the sciences. They're especially great for prediction tasks, so going from model to a realization of the data. Running a simulator usually involves going through a bunch of intermediate steps. These are latent states, which I've labeled Z. So that's why sometimes they're called mechanistic models, because you're mechanistically sampling for a bunch of intermediate distributions. So simulators are great for this. What we really like to use simulators for, on the other hand, is inference. And naturally, they tend to be rather poorly suited for inference, because going from an observation to understanding what parameters they are compatible with observation means integrating or marginalizing over a large number of intermediate states, Z. So that's kind of the basic issue with using simulators as inference tools. And simulation-based inference is basically a paradigm for trying to tackle this problem. Neural approaches to simulation-based inference use machine learning in smart ways to get at this. They basically combine the best of both worlds, mechanistic modeling, where you have some kind of simulator that lets you draw data samples. And the kind of key grokking moment here is the fact that when you're sampling from a simulator, you're actually sampling from the likelihood. You're sampling from P of X given theta. So there is some kind of underlying likelihood there that you can leverage. And the machine learning models are great at information compression, feature extraction, and they can be used kind of in different parts of the pipeline to get at either the likelihood or the posterior as needed. So, SVI basically lets us use machine learning to do this in a scalable way and use simulators to inject domain knowledge into machine learning models. So the specific problem I'll talk about on the physics side is learning the shapes of dark matter halos or density profiles using SVI. So the basic problem setting here is we have some dark matter halo, and we can parameterize or characterize it as a density function. So density as a function of distance from the center of the halo can be parameterized using an NFW or whatever. Traditionally, we might expect a cuspy halo, but a less dense at the center or chord halo can arise due to new physics or baryonic effects or what have you. And being able to do this mapping from here to here robustly is the thing we like to do. Of course, in real life, we don't actually see the dark matter halo. We see stars gravitationally bound to the halo. So the prediction task is what we want to do. We don't just want to do a prediction as like a mean or something. We also want to get a full posterior over this profile. And this is a challenging inverse problem because there's many possible configurations of stars that can correspond to the same profile. Traditionally, the way this is done is using dynamical genes modeling. So there we have, some stars gravitating around the dark matter halo. The stars can be characterized using a phase-space density, which is just a differential number density of stars as a function of position and velocity. Directly, we don't see the phase-space density. Something that's closer to the observables is the moments of the phase-space density, the velocity moments. So the first velocity moment, for example, is the average velocity. The 0th moment is the number density. The second moment, the anisotropy. And the Jeans equation connects moments of the phase-space density to the underlying potential. This is basically the continuity equation or the conservation of momentum applied to the system under assumptions like steady state equilibrium. So Jeans modeling is very successful, but it has limitations. For example, assumptions about the data generating process. So things like non-equilibrium effects, asphericity, baryonic effects, host potential. these are all challenging to include in the traditional genes analysis. There's other downsides. So the fact that we rely on low order moments of the Boltzmann equation in this case basically means that we're losing information. And typically we don't have access to the full phase space. We only have access to, say, the line of sight velocity and the angular coordinates. So this also leads to degeneracies between the dark matter density profile and the anisotropy configuration of orbits. This is not something that's super obvious, but just something that pops out. And in regimes where we have not a ton of stars to work with, the estimates for these quantities, the moments, are also noisy, and also the derivatives. So these are all things that propagate downstream to the analyses. I just get this. So the way we've been approaching this in a project led by Chien Wen, who's a student at MIT, who's starting as a postdoc at Northwestern soon, also with Lina Nassib, is using simulation-based inference for this task. So the specific method we use, which is fairly kind of common in this sphere, is called neural posterior density estimation. The basic idea here is to model the target posterior, in this case, the posterior over the dark matter profile parameters, using a machine learning model called a normalizing flow. This is just a flexible model that lets us estimate densities and evaluate likelihoods and things like that. And this model is conditioned on a graph neural network applied to the phase space coordinates of the dwarf galaxy. And also, as Tong had mentioned earlier, so this is just optimized using a log likelihood type objective, where the density of this posterior is jointly optimized with this graph neural network summary extractor. So what this does is give us a posterior estimator and also compress the data in a way that's most informative of the downstream posterior, without kind of boiling down to summaries like velocity moments. So what we get out of this is a posterior on the dark matter profile parameters, downstream the halo density, the enclosed mass. So in these plots, I'm just showing for a chord profile and a cusp profile example posteriors, given some true underlying density in the dashed red. And we can compare this with a traditional genes analysis. So on the left is a posterior on the slope of the inner profile gamma with the simulation-based inference method for a chord and cuspy profile. And on the right is, for the same system, doing this with the traditional genes-based modeling. So by leveraging more information, we can get more distinguishing power, for example, in these two scenarios. We don't have to restrict ourselves to assumptions like equilibrium, so more flexibility. And also this allows for a significantly faster analysis, because once we've trained the model, we can kind of deploy it whenever. So one of the things to be skeptical of these kinds of analyses is, does the posterior that you get at the end of the day actually make any sense? And this is maybe sometimes in contrast to traditional like MC cell analysis, where you have some of these asymptotic guarantees. So we can run tests like asking, if we simulate many, many samples from the same parameter point, get a bunch of posteriors, does the, for example, 68% highest posterior density contain the true value 68% of the time? And if that's the case, we should be for all the parameters on the diagonal. If we're off to either side, that's saying that our estimator is either overconfident or conservative. In this case, we seem to be doing okay. In more recent work, Tree's been applying this to more realistic kind of hydrodynamical simulations, so from Fireside. And as a very preliminary example, he's been finding that the GNN plus simulation-based inference method typically gets better recovery of the profile compared to using the more traditional genes-based analysis. All right, how am I doing my time? Doing okay on time. So that was half of it on simulation-based inference. In the second half, I'll talk about generative modeling. This is a totally different problem, so if you've dozed off, maybe to wake up now. It's also going from near field to kind of large scale structure, so a very different regime. Since we're in Santa Barbara, I wanted to mention my Twitter banner picture since last October is an AI generated image of way too many bikes in Santa Barbara. And there's a backstory to this that you should ask me about later. But this is just to make the point that, which I don't think I have to make, that some of these like generative AI tools are getting really, really impressive. We mostly think of them for like, creative or like illustrative purposes, but they can also be very useful for science, which is the point I'll try and make. So with some of these like text-to-image models, the way they work is using diffusion. So just in a very heuristic sense, the way diffusion models are trained is you start off with some data, some training data. You add noise to the data. This is a noising process. And you train a neural network to iteratively reverse that noising process. And you can condition this denoising process on anything you want, like a text prompt. So then at like deployment time, what's happening here is you're just sampling from P of image given text prompt, so likelihood. So you can maybe see already how generative models are useful for scientific applications. Generative models are basically simulators of the data, and the goal of generative modeling is to learn a probability distribution, P theta of x, that's as close as possible to some true underlying data distribution, P of x. And we might, we don't know what P of x is, but we might have some samples from P of x. And generative models, like diffusion models, let us learn an estimator for this distribution just based on samples. Once we have a good generative model, we can use it for sampling. So this is analogous kind of emulation, and also density estimation. So in the scientific context, this is like likelihood evaluation. The application I'll show is to galaxy clustering. So, distributions of galaxies measured, say, using spectroscopic surveys. So here the data is complex and high dimensional. Traditionally, the way this is done is by boiling it down to physically informed summary statistics, like the two-point correlation function. And simulations or semi-analytic models can be used to inform expectations of these summary statistics. And doing inference in this space is much, much easier than doing it in this space. However, doing this boiling into summary statistics means we're losing information. Also predicting what the expectation looks like typically involves simplifications. And one of the ways I think machine learning is exciting is being able to use more of the data and make fewer simplifications at this stage. So if we did have a generative model for galaxy clustering, what are some things we could do? One is emulation. So we could sample from the distribution of galaxies given cosmology, galaxy halo connection, descriptions, what have you. We also do inference. So if you have access to the likelihood, we can invert it, get a posterior on the cosmology. And also model evaluation. So we can try and understand how well does an observation fit within our space of simulations or within a forward model. So with Carol Questel-Zaro, who's another postdoc at IFI, we built a little generative model for galaxy clustering based on the Quixote simulations. Of course, these are not images, so you can't like pip install like stable diffusion and like just run your simulations. So this is a custom model based on either transformers or graph neural networks as the backbone. And so this is just an illustration of the noising process and the denoising process. And once we have this then lets us sample from the distribution of galaxies given cosmology, very analogously to the way text-to-image models draw from the space of images given a text prompt. And here's an example of this in action. So the diffusion process, starting from pure Gaussian noise, it might be a bit too bright to see, but forms a box. And we can vary the cosmology parameters. And if you squint real nice, you might be able to see the clustering configuration of the points change. And this can happen basically in fractions of a second. Since we have also access to a likelihood, not just a likelihood, but also a differentiable likelihood, we can use gradient-based sampling or variational techniques to go from something like this to a posterior. And because we're using more of the information beyond 2-point, we also generically see that we can get tighter constraints, which are the ones in tan here, compared to just 2-point correlation statistics, which is not very surprising. Okay, so that was not really very much to do with particle dark matter, but just as an advertisement. I'm kind of peripherally involved in this. So Tree took the code that we use for the large-scale structure emulation and applied it to Milky Way zoom-in simulations to emulate the distribution of satellite galaxies. And here's an example of that in action. So I believe the size of the spheres is the masses of the satellite galaxies. And this is very much in progress, but he's able to basically reproduce things like the abundance of satellites with correct dependence on things like the underlying warm dark matter mass and other kind of galaxy formation parameters. All right, so that brings me to my conclusions, which is just to showcase a couple of these machine learning-based methods to try and make more intimate the connection between forward models, which encapsulate some of the theory, and observations. Simulation-based inference is basically a way to invert some of these mechanistic simulators and generative modeling. Lets us capture the distribution of basically arbitrary complex, at this point, data, use it for emulation and inference. So thank you for listening.